Hello, everyone. My name is Pete Regas, and I'm from the McMahon Lab at Cornell University. And in this session that's titled YY03, which is titled AMO Qubits and Optimization, I'll be talking and giving a presentation based on this abstract that's titled Beyond the Variational Quantum Eigensolver, Approximating Solutions of 15 PDEs with a Variational Quantum Algorithm in Polynomial Time. To give a presentation overview, these are some bullet points which highlight in general strokes what the focus of the presentation will be on. First, we'll be looking at how we can introduce connections of our work with numerical methods for solving partial differential equations that are raised from the prospects and implementation of a recent variational quantum algorithm. And we'll demonstrate connections between polynomial runtime of this quantum algorithm that we've been able to implement in optimization in different optimization procedures. And finally, we'll conclude by providing examples of some simulation results for different ansatz for one specific partial differential equation of interest, which exhibits several different types of rich behaviors for propagating waves in solitons. And first, to get an idea about the specific quantum algorithm that we're going to be focused on, we can look at Lubash et al. This is a paper titled Variational Quantum Algorithms for Nonlinear Problems, and it was published by this group of authors from Oxford, and the first version of which was available in 2019. And some of the highlights of this work include introducing a new quantum algorithm that is able to provide high fidelity solutions for a few PDEs. And they first begin by discussing and explaining how their new quantum algorithm would be applied to obtain approximations of solutions to the invisiburgers in the Schrodinger equations. And from these two equations, it's left for us to wonder whether one could also obtain high fidelity solutions, or at least solutions of all right or of good quality to actual solutions for these same partial differential equations that have already been realized classically. And in doing so, we have to, the steps that their quantum algorithm rely upon is that the cost function has to be derived, which is expressed in terms of a superposition of quantum states and variational parameters that we optimize over, which is where optimization comes into play with our quantum algorithm. And we also will have to discuss and think about how the quantum circuit architecture and the qubits that need to be used for this optimization procedure as it relates to the quantum algorithm and how we can obtain different solutions to different partial differential equations of interest. And so to answer this question, I'm going to be referring to a recent preprint that I made on the archive around September some time ago. And the most recent version of this archive posting is from November, and it's titled Variational Quantum Algorithm for Measurement Extraction. And in this preprint on the archive, what I was interested in was first determining how many partial differential equations of interest we can solve with this new variational quantum algorithm due to Lubash et al., and how the behavior of and performance of the algorithm would depend upon the ansatz, which is our starting point in the Hilbert space that we would optimize over when obtaining solutions to different partial differential equations of interest. And as we had alluded to in a previous slide, it's very important for us to keep in mind the quantum circuit components that go into the algorithm and allow us to obtain quantum readout, which can be leveraged towards approximating solutions to different partial differential equations of interest. And to this end, we can look at the following depiction of the quantum circuit on this slide, which has 6 of the following components. The quantum circuit is read from left to right, and each one of the quantum registers are first initialized with a qubit that's given in the 0 state. And depending upon the structure of the quantum circuit architecture after this qubit that's initialized in the 0 state, we can either have a Hadamard test or unitary transformations, which can act on the qubit before it's either serving as an input port or a control port to the quantum nonlinear processing unit, or the CNPU. So besides the item that's first given in the 0 state, this qubit in the topmost register of this quantum circuit undergoes a Hadamard test, after which it can serve as ancilla qubits to registers to other quantum registers that are following in the quantum circuit, as well as being a control port, serving as a control port to the quantum nonlinear processing unit. And for all of the other qubits in the quantum circuit, which are initialized in the 0 state below the topmost register, there are also unitary transformations which are parameterized in the variational parameters lambda, which are given by u1 hat of lambda through ur hat of lambda. And each one of these qubits that is acted upon this unitary transformation can serve as one of the R input ports into the quantum nonlinear processing unit. And after we look at the action and performance or the action of the quantum nonlinear processing unit on these qubits, from the output ports, we can look to obtain readout for different nonlinear problems of interest, and we can obtain this readout by performing poly Z rotations that's given in item 6. And in the case of the topmost register, the Hadamard test is another operation that the qubit in the topmost register undergoes before we obtain readout from one of these registers. And another important ingredient that's important for our algorithm is the QFT ansatz, or the quantum Fourier transform ansatz, which is based on the ZGR, the Zalka-Grover-Rudolph ansatz. And this ansatz is important because it determines the initial state or position of the Hilbert space that we would like to explore before we compile the algorithm potentially 10,000s or hundreds or thousands of times to obtain the solution for our nonlinear problem of interest. And briefly speaking, the quantum Fourier transform ansatz depends upon a CNOT gate, a rotation gate, and Toffoli gates, which are more or less the same exact ingredients which appear in the quantum circuit architecture that was provided on the previous slide. And it's important because it's initialized before the first iteration of the algorithm is compiled. So we need this initial state to begin our quantum simulation. And for however many time steps of evolution we perform, this initial state that we have of our quantum solution will change and will become different as we continue compiling the algorithm in polynomial runtime. And as we had just mentioned, the optimization loop continues from the readout, in which we'll insert some distribution of poly Z gates amongst the registers in the quantum circuit over which we would like to obtain readout. And from this loop between classical optimization and obtaining in time evolving qubits that are given on our quantum circuit, we can obtain different approximations for various PDE solutions. And from our nonlinearity space of 15 partial differential equations, nonlinearities of the Kamasa-Holm equation exhibit many different behaviors. And the Kamasa-Holm equation is one PDE of interest that exhibits either, as we've reproduced here from a 2005 reference, the waves can either be smooth periodic, smooth with decay, or peaked periodic, peak with decay, in addition to several other types of more complicated behaviors. And the optimizers with polynomial runtime that we use that are able to provide us with useful insight for approximating solutions of the Kamasa-Holm equation include the Nevergrad optimizer, which is provided by Facebook Research, as well as different open source optimizers that are given by the Info, Snopfit, and Particle Swarm optimizers. And the Kamasa-Holm PDE is a third order partial differential equation, which is of the following form. We have U of t, which is the first time derivative of the solution, plus a term that's dependent on the first derivative of the solution, as well as all other remaining terms of the partial differential equation, which are dependent on the second and third derivatives of the solution. And we run the variational quantum algorithm for different initial conditions to determine whether any class of initial conditions exists for which the quantum algorithm can be ran in polynomial time, which we're able to achieve, as well as satisfying our curiosity as to whether the behavior of the numerical approximation to the solution, i.e. whether the solution oscillates more or less, or more quickly or less quickly at different points throughout the time evolution. And for different possible behaviors of standing wave solutions, we're able to obtain and realize solutions to the Kamasa-Holm PDE with the Nevergrad and particle swarm optimizers, as we had mentioned and introduced previously, for smooth periodic and peaked periodic behaviors, which can either be characterized by having a constant amplitude throughout the majority of the time evolution, or having some amplitude that can decrease or increase throughout the duration of the time evolution. And increasing the number of time steps of evolution yields quantitatively different results, in which if we allow for the time evolution to undergo for approximately 15,000 time steps, or even close to 20,000 time steps of evolution, with the Nevergrad optimizer, we're able to see that if we vary the time step of evolution, the amplitude and overall period of motion of the solution that we're trying to approximate can wildly differ. And our implementation broadly scales to 15 partial differential equations with varying nonlinearities. And we've listed these partial differential equations here. They have connections to many different problems of interest, whether it be fluid dynamics, gravitation, electricity and magnetism, nonlinear waves, or various forms of the KdV equation. And future directions of interest that we would like to explore along the lines of our discussion is whether there are other quantum algorithms with a more significant speed up in runtime, and correspondingly, how many qubits would be required for the optimization procedure, including the qubits that we would need to initialize for our ansatz, as well as the qubits that we need for the time evolution, which involves the quantum nonlinear processing unit. And finally, would quantum algorithms with faster runtime still deliver high fidelity solutions for different problems? And as for acknowledgements, I would like to thank Professor Peter McMahon, which is our principal investigator, as well as my colleagues Ali and Yilian. And are there any questions or comments?